last class I did give you a basic introduction of this, but anyway, we are just going to take a fresh start on this topic. We have the energy conservation, and based on this, we can say that the kinetic energy of the system before, let's say, the projectile hits the target, and after that, okay, should remain conserved. Also, that is the case with the momentum. So before we go into this, let's just look into the diagram now. We do have a projectile, okay. We do have a particle, maybe a neutron or a proton, and it will actually hit the target. So the target is at rest. So straight away we know that the kinetic energy of the target before collision is 0, okay. And this comes and hits, and then if we assume that it's a nuclear reaction, as we have said the other day, okay, and I also told you that how to actually denote a nuclear reaction, right? So we do have A hitting X, and then the outgoing particle would be B, and the outgoing nuclei would be nothing but. So the nuclei, the target actually has changed. It might happen because of a capture, okay, it might happen because of a stripping off reaction, and so on. So since there is a collision, then the chances are that the both of them will get deflected. And let's say the particle B, okay, gets deflected by an angle theta, and this is actually a detector. So this detector will detect this particle B. And on the other hand, the nuclei will actually get deflected by an angle phi, okay. It depends on what is the velocity with which it is coming, what is the mass of A, what is the mass of the target, and so on. Based on which this angle theta, phi, everything will depend, okay. So we'll just look into the momentum conservation first, and let's see what happens. So if you look into the momentum conservation on the right hand side, okay, on the left hand side, sorry, we do have only PA because that is the only particle which is moving, right? This is at rest, okay. After collision, what happens is we actually can consider the horizontal, divide it into the horizontal component and the vertical component. Before collision, what happens was that the particle A was only moving along the x-axis, okay. It was moving only along the x-axis, so it does have a horizontal component, but it does not move along y-axis, right? It does not move along this direction. So that means the vertical component would be nothing but 0. So before collision, the vertical component is 0, okay. So after it has collided, what happens to the horizontal component of the particle B, okay? So that means if you are considering this and considering the vectors, this would be your horizontal component of particle B, and this will be the horizontal component of Y. Both of them will be added up by momentum conservation, okay? This would be nothing but PB cos theta, this would be PB sin theta, this would be PY cos theta, and this would be PY sin theta. So I think these things we already know. So PB cos theta plus PY cos theta both will be in the same direction, right? So that is the horizontal component. What about the vertical component? We don't have any vertical component before collision, and after collision this will be PB sin theta. So the sine component will be along this because this is resolved along this axis, and the cos, the sine component for the phi part, that means that is for Y, it will be along this direction. So you see both of them are in opposite direction, and that's why using a minus sign, okay, and that is the vertical component, okay. So what is our aim? Our aim is actually to find out what is the kinetic energy of this particle B, because you know, if there is a nuclear reaction happening and there is an outgoing particle B, and if you can know about the energy of the outgoing particle, you can predict a lot of things about the system. So aim is to find out the kinetic energy of B, okay. So we are going to do that. So I think this is very clear, very simple. And then let's go into the energy conservation. So whenever there is a particle, okay, and if you consider the relativistic feature also, we do know that it will actually have a rest mass energy and then the kinetic energy, which is because of the motion, right? So we do have the rest mass energy before collision. So we do have the mass of the particle A and the c square, that is the rest mass energy of particle A, and then the target mass is mx, let's say, and then c square, so that's the rest mass energy of particle B, or x, right? So we consider this total, which is the rest mass energy plus the kinetic energy of A. Why A and not x? Because x is at rest. So this is something which is there. And you know, this kinetic energy is known. Why? Because we are controlling the reaction. We know how much field we are providing, how much electric field or magnetic field we are providing charged particle, based on which we can actually say how much energy this incoming particle has. So this kinetic energy is known to us. What happens after collision? After collision again, we do have the rest mass energy of Fb and My, that is always there, okay? And then the kinetic energy of B. Now B is moving, so that will be the kinetic energy of B, and of course the kinetic energy of Y. Of course, the kinetic energy of Y. Okay. So there is an aim here why we have written this in terms of Py square, because we are going to write down this in using this equation, these two equations. So we already know kinetic energy is equal to nothing but P square divided by 2m. So that's why I've written it as Py square divided by 2my. Okay. So let's just keep this in mind and let's try to simplify things further. What we do now is we are going to do slight adjustments here. Okay. First thing, if you are taking the rest mass energy on this side and the rest mass energy on this side, okay, you can subtract this rest mass energy from this rest mass energy, and in a typical reaction this will actually give you the Q value. So that's your Q value or the Q energy, right? So we just write it down as Q. Okay, so we have just simplified things. We have just considered the two rest mass energy, one minus the other, and that is your Q energy or value. That happens in a typical reaction. Okay, you also study this part in chemistry. And then what else is left? We have Ka, so we've kept it Ka, this is A not alpha. And then we have got Kb, we've kept it as Kb. And 1 divided by 2 My Py square. So Py square we can actually modify. Okay, Py square can be written in this way. How? You see this, Py sine theta is equal to Pb sine theta. Okay. See, y is something which I don't know, okay, about the target. So I'm going to find out what is happening to B and not to y. So if you look here, Py sine phi is equal to Pb sine theta. We can just keep this. And here also we can write it down, Py cos phi is equal to Pa minus Pb cos phi. Okay. So if we do that, what we have is this equation. Py cos phi is equal to Pa minus Pb cos theta, and Py sine phi is equal to Pb sine theta. We can square and add both sides. So we can square and add this. If you square and add cos square theta sine square phi cos square phi will become 1. So this will just become Py square. And on this side, you will just have this stuff, this square plus this square. Okay, square and adding. So that's why I have put this particular equation. So I think it should not be very complicated. This is a simple conservation of energy, conservation of momentum problem. Okay, but then the analysis that we are going to do in terms of nuclear physics is quite priceless. Okay. So we have this Q plus KB, Ka is equal to KB plus 1 by 2 Mi. And then we can actually open the bracket. So if you open the bracket, you see this Pa square you'll have. So Pa square is there. And then you can have Pb square cos square theta, and then there is a Pb square sin square theta. So you just add them up. Cos square theta, sin square theta will become 1. So this is just Pb square. And then of course there is a minus sign because of this, minus of 2 Pa Pb cos theta. So minus of 2 Pa Pb cos theta. Okay. But suggest that all of you write these things down and practice it on your own. That's very important. Okay, step by step. Okay, so you see this is actually slowly turning out to be a quadratic equation. Now let's see how we write down this or arrange this quadratic equation. So this Kb plus Ka Ma by My. I think this is not very complicated. This My is there. This My is this My. Okay, and then this is Pa square divided by 2. Okay, so you know that kinetic energy, right? Kinetic energy, let's say K. Okay, like no problem. I think this is already known to you. We need to explain much. This is 2p square divided by m, right? Last time also we saw divided by m. Okay, so this is 2p square divided by m. Okay, so if I take a divided by 2m, p square divided by 2m, right? So there is already a 2 there, so it is p square divided by 2. I just need an m here, so I'll just divide and multiply by ma. So ma multiply and divide, and that term will give you the kinetic energy. So this is Ka ma by ma. So just do the math, simple. Okay, verbally you can do it. And similarly, this is Kb mb by my. We're interested in finding out the kinetic energy, that's why we're writing it down in this form. Okay, then minus. Okay, now look here. So if you just multiply this and this, you do have the 2my here, and then there is a 2 here, so this is this 2. Okay, and then cos theta, this cos theta. So you can just simply do it. It will be cos theta by my, and whatever is left is kept. Okay, so what is left here is nothing but Pa and Pb. So we know what is P. P is nothing but root over of 2me. So we can write it down 2me. So that's k, okay, representing it by k, the kinetic energy, root over 2mk, let's say. So this is root over 2mkb, and this is root over 2mka. That is written for PA and PB. So this is PA, okay, and then this is PB. We just do this modification, and we see that everywhere we do have a KB. We have a KB here, we have a KB here, we have a KB here. So that means the kinetic energy of B can be found because we are getting a quadratic equation. Okay, so we will look into this. What we can do is this: we can just simply take KBs together. So if we take KB here, we have got 1 this term, okay, and then plus MB by MY. So this is there, MB by MY. So this is this term, right? So this is done, KB is done, and then minus root KB. So you see this is a root KB. So this root KB can come out, okay. Whatever is left is nothing but cos theta by my, which is cos theta divided by my. This is 2 into 2, which is 4. So out of the root, so it becomes 2, and root over, this is MA MB. I should have written MA MB here, okay, but anyway, so I think it's understandable here. MA MB into KA. So this is there. Whatever is left will be a constant because I know already what is the kinetic energy of the particle A. So Ka Ma by My A energy. So Q energy is also known to me. Okay. If I know the reaction, I can actually predict the Q energy. That's simple. Okay. So this is the equation that we have finally. Okay. And if you do the maths, okay, you can just say that this will be nothing but equal to 0. Okay. This is not implies here. I think this is. If I just do it, I can just arrange it. Okay. So this is there. Okay, I've taken it this side, so we can actually put it as 0 also, no problem. So just do it. Okay, there might be some mistake with minus and plus, but I think it's okay. Then what we do is we can actually divide throughout by my, just simplifying things, nothing else. Okay, just simplifying things. On one side it's 0, I'm dividing throughout by my, so this will be my plus mv, and then there is already an my here, this can be multiplied. They are also already an my. The only part is we don't have an my is here, okay, and here. Okay, so what you can do is ka can be taken common. Okay, here ka can be taken common, and my minus ma minus qmy is equal to 0. So this is what you have to do. Okay, and then what we do, we actually solve it for the quadratic equation kb. And if you basically solve it for kb, you know this is an equation here. Okay, then there is a root kb here, and then there is a kb here, and then there is a constant here, the entire term. Then you can use the formula b square minus 4ac divided by 2a, and then basically you can find out what is your KB. Okay, so this is how it is solved. So of course it looks like a bit complicated, but then if you have all the parameters, it should not be very complicated at this level. Okay, there are computers and all which are basically used to solve for this kinetic energy. Okay, and then the prediction can be done. Okay, because this is the kinetic energy, so where is the remaining energy gone? So these kind of calculations are also helpful for detecting unknown particles. Let's say how is neutrino detected? Okay, because there was no conservation of energy observed, so there must be an additional particle after which there is conservation of energy. So that means unknown particles can also be detected if we do these kind of analysis. So that